Hello everyone, and welcome to this week's Crunch seminar. Our first speaker today is a person who is known to most of us, an old Crunch member. She is Dr. UAU, who's currently the associate professor at the Department of Mathematics at Lehigh University. She is an old Crunch member. She completed her PhD at Brown at Crunch Group. She is affiliated with the College of Health and the Institute of Data and Intelligent Systems and Computations at Lehigh. She's particularly interested in applying mathematical analysis knowledges in the design and analysis of mathematical models and numerical systems. And with this, please join me in welcoming Dr. UAU. And without any further ado, you may want to start, UAU.
Yeah. Thank you so much, Sandata. Yeah. So first, I want to thank George and Sandata for the kind invitation. It's truly an honor to introduce our work here. So today I'm going to talk about our work on the continuous optimization methods for learning Bayesian networks. So basically, firstly, I'm going to talk about what is the Bayesian neural net, or what is the Bayesian network, and why is that associated with one special type of graph called the direct cyclic graph, or DAG in short. And then I'm going to talk about some benchmark methods in the Bayesian network, structured learning, or DAG structured learning in short. And then one of the new type of the method, a new breakthrough in this area, is the so-called continuous optimization method. Then I'm going to introduce three of our recent work on trying to improve the efficiency and accuracy for the continuous DAG learning methods. Yeah, so I don't know how many of you guys are a soccer fan here. So so here, so from this example, probably you can recognize these two soccer players. So now I'm going to use that as one example. So basically, if we have several events, so for example, like Karim Benzema joined the Real Madrid, like maybe Messi quitted the national team, like France economy slumps, like UK left the European Union. So all those events. So what does the Bayesian network is trying to do? It's actually trying to give a probabilistic graphical model that represents the conditional dependencies of multiple events, which is modeled by a set of the random variables. So for example, here, when we have the random variables, like n numbers of the random variables from x1 to xn, then it's going to write the joint probability of these n random variables as basically a product of several local probabilistic distribution. So that means each of the random variable depends on it's what the so-called parent random variable. So then you can see those parent random variable as the cause of an event, and then the triad random variable, you can see that as the result. So by doing so, then we can see that the Bayesian network actually has many important applications, and one of the application is the causality, so basically the causal structured learning. So that means given an event that occurred, so the Bayesian network can try to predict what is the likelihood that one or several known causes might be the contributing factor. So now let's go back to the example here. So well, we know that UK left the European Union, right? Can maybe Benzema joined Real Madrid can be one of the costs. So this example might seem really crazy, right? But however, it can have a logic chain like the following. So we might say, well, maybe because Benzema joined the Real Madrid, and because of that, so France economy slumps. So that's basically the Benzema joined Real Madrid caused the French economy slumps. So connecting to this note. Oh, sorry. Yeah, here. So then because of the French economy slumps, so French doesn't work with UK anymore. So that caused UK left the European Union. Of course, this is just kind of a funny example. This cannot be true. But what we can see here is, well, this causal relation. So this kind of the conditional independence can actually be encoded by directed edges between different nodes in a graph. So basically, we can let each of the calls pointing to the result, and then by doing that, this directed edge actually represents the causal relation and also represents the conditional dependency. So that's the first property that is associated with the Bayesian networks and the graph underneath that. So it has directed edges. And then the second one is, well, we know that Benzema joined Real Madrid first, and then French economy slumps, and then UK left the EU, right? But however, can we now, if I ask a question, is that possible that because UK left the EU, then because Benzema joined Real Madrid? Then of course we know it's not possible because UK left EU after Benzema joined Real Madrid. So that means, well, for this causal relation, there is no cycle. We cannot say A cause B and B cause A too. So that actually induced the second important property of this Bayesian network. So that is the associated graph should be acyclic. There shouldn't be like a causal cycle inside that. So that means, well, we already know that there is a train from Benzema joined Real Madrid to UK left the EU, but then we know that UK cannot be like, there cannot be a directed edge from UK left EU to Benzema. Okay, so yeah, so we have been talking about kind of the funny example. So now let's talk about some maybe more realistic example. So yeah, so hopefully from that funny example, we have already seen that, well, the Bayesian network basically is it's associated with a directed acyclic graph. And this directed acyclic graph expresses the conditional independence relationship among the variables in the Bayesian network. So so maybe let's to see the relation between the Bayesian network and the underneath probability distribution of these random variables. Maybe let's now try to see an example in the knowledge graph, like from the royal family. So this is an example, like for example, if we already have a graph for a knowledge graph for the royal family. So firstly, what is the knowledge graph? Knowledge graph basically, intuitively to represent knowledge. So in this graph, each of the node is an entity. So for example, here, each of the node are actually a family member in the royal, a member in the royal family. And then what is the edge between them actually represents the relation between them. So yeah, so knowledge graph, as we are going to return later to this example, is one of the application that, well, we can try to try to infer what is the, for example, maybe the missing components in this graph. So for example, if I'm a Wikipedia, but I don't have enough knowledge about, well, for example, has Elizabeth got married before, or has Elizabeth has or had a spouse? So, but however, how can, from like a human being point of view, if you ask me this question, like, how likely is Elizabeth has got married before? So I can try to search my data. Well, I can see, well, Elizabeth, although I don't know if she has a spouse or not, but however, like this purple edge, it's missing. But however, I know that Elizabeth is a parent of somebody. And I also know that Elizabeth has several sons. So then from those, then maybe, from a human being point of view, I can see, well, very likely that she had a spouse, right? Otherwise, she cannot be a parent. Otherwise, although it's still possible that she can be a parent, but the likelihood is much lower. So yeah, so that is basically what the knowledge graph and the knowledge graph discovering is trying to do. So, but however, how does this relate it with what we are trying to? How can we try to get a mathematical model from there? So we can represent each of the event. So basically somebody like Elizabeth is the parent of somebody, Elizabeth has sons, Elizabeth has a spouse as different nodes, as different events. And then we can try to get what is the joint probability of those events and the kind of the parent events. So for example, our node 3 represents like if Elizabeth has sons. So then the probability of that being true is, for example, like 20%. And the probability of that being false is like 80%. And then we know that, well, if Elizabeth has a son, then possibly very likely she's also the parent of somebody, but not vice versa, right? So therefore, we can draw a directed graph from node 3 to node 1, and then we can also list out the joint probability between them. So for example, if Elizabeth doesn't have a son, if somebody doesn't have a son, then it's still possible that he or she can be a parent. But however, if he or she does have a son, then it's like 99%, very, very high probability that he or she is a parent of somebody. And similarly, if we already know that, well, this person is a parent of somebody, if this person has sons, then we can have the joint probability. We can infer that, well, very likely this person has a spouse or had a spouse. So then if we want to represent that as a joint probability function, how do we write that? So that is the Bayesian network. So basically our node 2, the probability of our node 2, event 2 depends on event 1 and 3. So that is the first part, and multiplying the probability of our node 1 depends on node 3 and the node 3. So from here, we can see that the directed acyclic graph, so basically the direction of these edges is naturally correlated with the joint probability function. And once we have this directed acyclic graph, this graph structure behind those events, then it will actually help us to actually write the global distribution, probability distribution of those random variables into a product of many local probability distributions. So yeah, so maybe to see it more concrete, maybe let's try to mathematically formulate this problem, the Bayesian network learning problem. So basically for this Bayesian network learning, we are trying to learn from a bunch of the norm samples. We try to learn what is the underneath joint distribution and also the underneath the DAX structure for that. So namely, we have given that we have n numbers of random variables, and those random variables will be the nodes of this graph. Then we are trying to learn the edge, a set of the directed edges, which we represented as E behind that, such that this edge they should be acyclic, meaning there is no cycles in that. So where do we try to learn that? We try to learn that from samples. So that means, well, even if I'm an AI, how do I know that if somebody is a parent, then very likely this person should have a spouse. How do I know that? The way I can know that is maybe from the other components of this graph. Right. So for example, if I try to, I don't know if Elizabeth had a spouse or not, but maybe let me try to observe what about Prince Philip. So Prince Philip is the parent of, like, say, Prince Edward, and also he has a son. So from there, we can collect the data. So for Prince Philip, he's the parent of somebody. So the first node is the value for the first sample. The first node is equal to 1. He has a spouse. So the second node is also 2. And he has a son. So the third node is also 2. So by doing that, we collect the data. So now we try to check the second, maybe the second part, the second sample we can collect. So maybe this is a person who is a parent, who has spouse, but who has a daughter, so no son. So therefore, this sample will be 110, and so on. So our goal is, by given n numbers of identically distributed samples like this, so like a vector with like m components, we are hoping that we can try to recover the underneath DAG structure. So that means basically the graph on the right. So now, but mathematically, how do we represent the DAG structure? So we represent it with what we call the weighted adjacency matrix. So here, for this weighted adjacency matrix, each element is non-zero if and only if there is a directed edge from node I to node J. So for example, here, if we have, well, the node 1 has, so if we already know that node 3, so basically has sums, is going to induce to like possibly who this person is a parent of somebody, or this person like has a spouse. So then for the third for the third row, then we are going to have node 3 has a directed edge to node 1. So therefore, the first element should be non-zero. I mean, in reality, it doesn't have to be 1. It can be any real number which is non-zero, and this real number can characterize like how much correlation is that B between these two variables. So then the second one also similarly, the second element similarly. Then we know node 3 infers to node 2, so therefore there is an element which is the non-zero here. The second element is also non-zero. So therefore, now the mathematical problem becomes the following: given n numbers of random variables, that those are the entities, those are the random variables, and then given like n numbers of IID samples on those random variables, what we want to learn is basically the directed acyclic graph between those random variables, which is characterized by a weighted adjacency matrix. So this weighted adjacency matrix should be associated with a directed acyclic graph. So that means there should be no cycle in the way. If we try to draw a graph from this weighted adjacency matrix A, then there should be no cycle from there. So yeah, so basically that is the classical or the mathematical definition for the Bayesian network and the DAG structure learning from there. So but yeah, so then maybe before we jump into the method that we have developed, let's try to see what are the conventional DAG learning methods. Conventionally, there are 3 types, mainly 3 groups of the DAG learning methods. So the first one is called the constraint-based algorithm. So basically, it relies on the independence test, which shows the existence for each edge. And yeah, so the drawback of that is, of course, you have to check for each edge, and also when the graph becomes large, like the knowledge graph we have seen, like maybe we have like lots of entities. So in that case, the high order independence test becomes extremely challenging. So yeah, so that actually makes the constraint-based algorithm, it's when you have lots of data and also the graph is relatively small, constraint-based method will perform well, but it's challenging to handle a large graph and also a limited number of samples. So the second one is the score-based algorithm. So the score-based algorithm is slightly different from the constraint-based algorithm. So constraint-based algorithm, because you try to check for each edge, so it can be seen like a local method. For the score-based algorithm, it's trying to learn maybe more like a global structure. So basically, it relies on the score on the whole graph. So therefore, it has the consistency guarantee. But however, one of the drawback is, again, if the graph becomes very large, then actually the score-based algorithm, it actually becomes an optimization problem on basically a discrete constraint. So that makes actually makes a really huge searching space and makes the score-based algorithm also very challenging traditionally. So the third type of the method is the hybrid algorithm. So that means, well, just trying to combine the two above. So for example, one can try to use the constraint-based algorithm to try to identify some of the edges and maybe remove some of the edges. And then by doing that, we actually reduce the searching space. So then the next, maybe the second step, one can try to use the score-based algorithm to try to like modify the results, to try to give some further correction. And and also another possible way is maybe somebody can run the score-based method to get some very coarse search, and then try to prune the edge using the independence test. So so here I try to list some of the. I mean, this is not an exhaustive list because this area has been developed for many years. But however, these are some of the state-of-the-art methods, like for each of the category. And later in our numerical examples, I'm going to also compare our methods with some of the example methods here, which are highlighted by the bold color. So okay, so then because the score-based method it's kind of can be seen as more global, it guarantees consistency and also generally more accurate, especially when the data is very limited. So therefore, in this talk, we are going to focus more on the score-based stack learning methods. So for the score-based stack learning method, as we have been talking about before, it becomes very challenging when the graph is large, when you have lots of nodes. So therefore, traditionally, the stack learning method is actually the so-called NP-hard. So the conventionally, they are like two main strengths of the stack learning method, of the score-based stack learning method. So one may make some parametric, for example, Gaussian assumptions, but this type of the method can only be applicable for the continuous variables, and also it might result in model misspecification. And the second one is, well, you just simply perform the score at the search based on the discrete variables. So that means, well, we try to do optimization problem. So here F is the score, A is basically the weighted adjacency matrix, and X is our data. So, but however, we want to constrain the graph to be acyclic. How do we do that? So that becomes a discrete constraint. So if we don't do any, like say, further modification, then this problem itself is actually a combinatorial optimization problem, because given n nodes of the graph, then the searching space will be in the order of the factorial of n. So that's extremely huge. If, for example, you are handling something like a knowledge graph, which has like thousands numbers of nodes. So yeah, and then in 2018, there is a breakthrough in this area for the score-based stack learning method, which we call no tiers, or that is no tiers. So this method, what they are trying to do is the following. They try to rephrase the constraint as a continuous constraint. So that means instead of doing the discrete constraint that the graph has to be in the DAG space, but however, it's trying to say, well, so the authors has shown that as far as the weighted adjacency matrix satisfying such an equation that HA equals 0, then it's guaranteed that the associated graph, the corresponding graph, must be a DAG. So the advantage of that is now it becomes a continuous constraint optimization problem, right? So basically the loss can be continuous, the score can be continuous, and also the constraint is also continuous. So then many conventional constraint optimization problem can be applied. So for example, like the augmented Lagrangian method, and that's also exactly what no-tier has employed. So before we jump into the methods and also the problems of no-tiers, so because that's will be related with our method. So maybe let's briefly see what is the key steps in the proof for no-tiers. So the idea behind this proof is also quite simple. So they start from like a graph. They start from a graph a matrix with the elements zeros and ones. So 0 means there's no edge, and 1 means there's an edge between node I and node J. So then here they try to, so then how can we try to count the number of cycles in this directed graph? So what one can do is, well, if you take the piece order of the associated matrix and take the trace of that. So one of the classical results is this trace will actually give you the number of the length p cycles. So therefore, as far as we can make sure that for from p equal 1 to m, then this trace is equal to 0, then it's guaranteed there is no cycle in this for this graph, for the graph associated with p. Right? That's the classical result. So what the Dagnotier group was trying to do is the following. So they think, well, I mean, we don't have to have the b to be ones and the zeros. Actually, it can be any positive. I mean, it can be any non-negative matrix. So that means as far as each of the element is actually non-negative, then we can do the same thing. But now this time, the trace of a to the piece is no longer basically the number of length p cycles. It actually becomes a weighted length p cycles. That means it will be the summation of each cycle multiplying the weights. So that is the weights of the weights is actually identified by the edge value. So so therefore, by doing that, we can, as far as we can make the weighted adjacency weight matrix of a graph to be positive, to be non-negative. So for example, we can let the matrix do the Hartman product with itself. Then it will be guaranteed that each element will be non-negative, and still keeping the property that if the value is larger than 0, then there is an edge. If the value is equal to 0, then there is no edge. So then we can try to apply this trace to the power of this Hartman product. And then as far as we can make sure that the trace of the power of this Hartman product to be 0 for all possible numbers of cycles, then we can still guarantee that the associated graph has no cycles. So mathematically, how can we do that? We, instead of, I mean, in Dagnotiers, they try to do the following, because if you try to do a Taylor expansion, then exponential can actually be the summation of like the power of a matrix divided by the factorial of the related power. So therefore, as far as we can guarantee that this trace, I mean, each of the power in this trace is equal to 0, except when p is equal to 0. So when p is equal to 0, the trace will be equal to the a dot a will be actually identity, a dot a to the zeros will be identity matrix. So the trace of that will be equal to m. So that is the total number of nodes. So then therefore everything else except p equals 0, the trace will be equal to 0. And then that's equivalent to be the trace of the exponential of the Hartman product of a and itself to be equal to m. So here m is the number of nodes. So that's how in Notiers the authors can try to transfer the discrete relation to the discrete constraint to a continuous constraint as HA equal to 0. So like I said, because this is a continuous optimization problem, so that actually enables many of the interesting application of like classical optimization methods. So for example, augmented Lagrangian method. So the augmented Lagrangian method like is defined as the following. It's trying to update for A and also for the Lagrangian multiplier, which is denoted as the alpha here. And then there is a penalty, which is denoted as rho divided by 2h squared, which is applied to enforce the positive definite of the Hessian of the Lagrangian. So that means to guarantee that, well, this method is actually has the better, like the convexity property. So But however, as I'm going to step into more details, so in practice, we found that this augmented Lagrangian method for no tiers, actually it takes many steps to converge. So that means you have to put the penalty has to be extremely large to make it convergent. So that means until this penalty becomes like in the orders of 10 to the 16, we don't really see that the graph, the estimated graph becomes close to a deck. So, and another issue of the no tier is it only handles the linear structure equation. So that relies on the assumption that, well, each node is linearly dependent on its parent node. So here the Z is basically a vector representing the noise. So yeah, so therefore.
Hello, Yu.
Hello. Yeah.
I have one more question. So you.
Yeah, please.
Yes. So you mentioned that the penalty should go to the 10 to 16. But I remember, so for augmented Lagrangian, for convergence, we do not require the rho go to infinity, right?
Yeah, exactly. That's the problem I'm going to talk about. So yeah, so later we are going to see that it's actually because no tiers doesn't satisfy the KKT condition.
Oh, I see. Okay, thank you.
Yeah, so then we try to propose that's exactly what we do in no fears. Yeah, you can see everything we call diagnose something. So yeah, so then in no fears we try to propose an alternative formulation that satisfies the KKT property. So try to fix this issue, this convergence issue with no tiers. Yeah. Okay. Yeah. Thanks, Lu. So that's a great question. That's exactly what we try to resolve in one of the methods. So based on that, we try to propose 3 types of the method. So the first 2 methods are actually trying to handle this slow convergence issue, which we call diagonal fears and the diagonal curl. And then the second method, and then the last method, I mean, if I have time, I will also explain our last method. So basically, we are trying to combine the direct learning with the power of neural networks. So, and then we develop a method called the DAX-GNN, which can handle more complex distributions and also different types of the data variables. So for example, like discrete data. Okay, so firstly, that's the diagonal fears. So yeah, so like what Lu has asked it, this is for the classical, I mean for the classical result for the augmented Lagrangian method, I mean this really shouldn't happen because classically, theoretically, I mean the augmented Lagrangian method should approximate well the solution of a constraint optimization problem without increasing the penalty parameter rho to infinity. But however, it turns out this is not true for the diagonal tiers. So in practice, we found that diagonal tier doesn't converge, even if we increase rho to 10 to the 16th. So that means we have to solve this unconstrained optimization problem like many times and do such an iteration, try to update the Lagrangian multiplier, trying to update the penalty coefficient, and until the penalty becomes extremely huge. And also even worse, if the rho becomes really large, then it will cause this augmented Lagrangian method to be very poorly conditioned. And also the optimization solver will take a really long time to converge. So that makes that the diagonal tiers become very slow, especially when the rho is especially when it's getting closer and closer to the convergence. But why this is happening? So to see that, we try to revisit kind of a classical result in the optimization. So that's called the KKT conditions. So the KKT conditions is actually the so-called the first derivative test for the solution and to be optimal. So basically the KKT conditions has 4 components. So the KKT condition is actually telling us, well, the solution should, one of the necessary conditions is the KKT should satisfy these 4 properties. So the optimal solution once satisfying these 4 properties, then we are going to say, well, it satisfies the KKT conditions. So the reason why that node here doesn't perform well is because the KKT condition, as we are going to show soon, we found that the KKT condition is no longer necessary for the node tiers. So because KKT condition is no longer necessary, so there might be some local or global minimum that doesn't satisfy the KKT in the node tiers. So therefore, however, the optimization method is related to satisfying the KKTs. So that means we might never find those optima. So why is that happening? What's go wrong? So actually what went wrong is the first condition, this stationarity condition. So yeah, so to see why it went wrong, we can see the following. So basically, we can try to, so basically one of the fact is if B is basically a positive weighted adjacency matrix, and then if we take the gradient of basically this constraint, the deck constraint H with respect to B, then the ij nodes is equal to 0 if and only if there exists. It's non-zero if and only if there exists a directed path from node J to node I. So what does that mean? That means, well, if A is a deck, then there shouldn't. If there is a directed path from node J to node I, then there shouldn't be any edge from node I to node J, and vice versa. That also holds. So therefore, the first thing we can show is if A is a deck, it happens if and only if like B dot the gradient of B of this deck constraint should be equal to 0. So now if we take this B as the hardbar product of A and itself and try to do a little bit transformation, then we can show the following. As far as A is a feasible solution, means A is associated with a deck, then we must have the gradient of H of this deck constraint with respect to A is equal to 0. So yeah, now it looks still okay, but now if we try to revisit our stationarity condition, then what do we have? The stationarity condition tells us, well, basically the gradient of the loss plus like the Lagrange multiplier times the gradient of A times U is equal to 0. So that means if A is a deck, if A is a feasible solution and also satisfying the KKT condition, then we must have the gradient of H with respect to A is equal to 0. So that means we must have the gradient of F with respect to A is also equal to 0. So what does that mean? That means, well, A is a feasible condition and also satisfying the KKT condition, and also being and also satisfying the KKT condition, then A must be an unconstrained stationary point of our loss function F. So that means unless A is a constraint, like stationary point of the loss function itself, then otherwise it cannot be a stationary point for the augmented Lagrange method. So that implies the following. So the first is the acyclic solutions, A cannot satisfy the KKT conditions. So KKT condition is no longer a necessary condition here. And also the augmented Lagrangian algorithm. So because of that, the augmented Lagrangian algorithm cannot converge to the acyclic solution, even with a very, very high penalty. So that's why we see that this penalty, this rho has been increasing like until 10 to the 16th, but still has no convergence because the KKT condition is violated in this problem. So the acyclic condition, I mean, doesn't satisfy the KKT. It couldn't converge to a cyclic solution. So yeah, so then well, we find the reason why that node tiers doesn't converge well, right? Why the augmented Lagrange multiplier method went wrong here. So, but a more important question is, how can we try to fix that? So to fix that, so maybe quickly go back to the proof of the acyclic constraints. So we see that one of the possible reason here is, as we have shown in the proof, because in the acyclic constraint, we are taking the exponential of the Hartmann product of A and itself. So because of that, we have, such a property that a feasible condition, the feasible solution, a DAC, must lead to the gradient of A and HA equal to 0. So therefore, we are thinking, well, maybe we should modify the DAC constraint. We shouldn't use the Hartmann product. So to see that, let's try to see how can we relax this condition. How can we try to modify the Hartmann product A? So why they are using the Hartmann product here? It turns out from this proof, we can see that the only reason why is they want to find a matrix which is non-negative. And also this matrix should satisfy the property that, well, each of the edge is non-zero if and only if the original A, the edge of the original A is also non-zero. But however, we have other options, right? We can do other options to modify that. So yeah, so so that is the first thing we try to do. So maybe we can, you can take any matrix that is related with A, and the value of this matrix is non-zero if and only if, like, the original Aij is non-zero, then it will do the same job. And the second property we have observed, we try to modify is, well, the original one is trying to use an exponential, right? So, but however, the exponential, when the matrix becomes large, then it's kind of going to grow like exponentially. So the second property we are trying to impose is, well, even if using the exponential, but actually for any like p larger than n is actually wasted. We don't need that because there's no possible for this matrix A to have a size n+1 cycles. It only has m nodes. So therefore, we try to replace that with a polynomial acyclic constraint. So now here is our proposed method. We propose, well, instead of trying to use the exponential, maybe we should instead use the absolute value of A. If we are using the absolute value of A, then we can see it does the same job, right? The Aij is equal to 0 if and only if the absolute value of Aij is equal to 0. So, but however, now you might still complain. So, well, Aij is, if you take the absolute value, then that means the problem, the optimization problem or the constraint, actually the smoothness that get damaged, right? So it's going to be, it doesn't have a continuous derivative. So how can we, so therefore we propose a further modification. Instead of solving for the absolute value of, trying to use the absolute value of A, we try to decompose A into the positive part and the negative part. And then we can rewrite A as the positive part subtracts the negative part. Then the absolute value can be written as the summation of the two. So now we can see that we are still have a continuous optimization problem with the continuous constraint. And then we can try, so then that's our proposed method. So instead of trying to use the original node tiers, which depends on the Hartmann product of A, we try to use such a decomposed positive and the negative. We solve for the positive and the negative components of A. And then, so, meanwhile, we try to apply the constraint to their summation, which is equivalent to the absolute value of A. So, and even better, we can show that, well, for this formulation, a feasible solution, although to this is actually not quasi-normal, but however, the KKT condition becomes necessary and sufficient. So, yeah, so that means basically if we try to run an augmented Lagrangian method based on this formulation, then actually we can expect that it will converge before rho gets to like a very huge number. So yeah, so and also so then I'm running out of time. So now we are trying to use this formulation firstly, like to do the direct optimization. So yeah, here I'm just going to quickly show this result. So therefore, but however, from here, what we can see that here the no tiers, the red line is the original method, the original continuous optimization method for the deep learning, and the blue line is our method. I mean, without doing any using basically a random initialization. And here the FGS are the fast greedy search, and HCPC are actually all the basically the.
Can you define the benchmark? We don't know what you're looking at. What is the benchmark?
Okay, yeah, the benchmark result is no tiers. So you can see that the asset. So yeah, sorry.
No. I mean the problem. What the problem we are looking at?
Oh, I see.
Not the method, the problem.
Okay, so for this one, it's still the synthetic data. So basically, the data are generated by the following. We assuming that the data has actually a continuous. So for each of the nodes depends linearly on its parental nodes. So therefore, it satisfies the so-called linear structure equation model. So therefore, the data is generated as below. So I mean, in practice, we do the following. So firstly, we generate a ground truth like DAG, a ground truth graph. So that is the A here. And then we try to sample a bunch of the Z. Then from A and the Z, we try to generate the X. So so for this given A, we generate a bunch of the samples X. And then we try to see if from this X, we can recover our ground truth A, which is assumed to be unknown during the learning. So this is a linear structure equation model, actually.
Okay, thank you.
Yeah, thanks. Sorry, I actually explained that. So yeah, so then how do we characterize the accuracy? Yeah, sorry, I should also explain that. So the accuracy is characterized by the structure harmony distance, or SHD. So intuitively, SHD tells us like, well, how many operations, for example, you can add an edge, you can delete an edge, how much operations does that need from your solution to the ground truth solution or the ground truth graph. So of course, this SHD, we can see that as an error, the smaller, the better. So the x-axis is the number of the nodes in the graph. And so the larger the graph is, then the more challenging this learning problem becomes. And then here, the ER and the SF are two different types of generating the graph. So one is slightly, maybe like I would say denser. So that's the SF, and the other one is maybe slightly like more evenly distributed. And here the number here represents the average number of edge for each of the nodes. So the larger this average edge number of edge is, then the learning becomes, that means the graph is more dense and the learning becomes more challenging. So therefore, what we value more is, for example, like ER4 and SF4. So that actually kind of more, and when the D is close to 100, so that's a relatively large and a dense graph. So yeah, and here we can, so basically here what we are trying to say is, although our KKT formulation, it looks good, but however, still it doesn't beat our baseline method. So that is the no-tier. So we suspect that that's because no-tier actually has better smoothness because of its quadratic adjacency. So therefore, what we really try to do is, one of the remedy we try to propose is, well, we know that the no-tier performs when the rho is small, when the penalty is small, no-tier doesn't have a big issue, but it really becomes problematic when the density becomes large. So therefore, but however, that's actually the region that our new formulation can actually help. So that's the reason why that we propose to the so-called no fear. So we try to use our KKT formulation as basically a post-processing method. So that means we can firstly try to run no-tier maybe for like several iterations to get a good initialization. And then we try to use the KKT formulation to kind of continue from there. And by doing that, we can finally we finally have very, very good results. So here on the upper, I'm showing the SHD, so basically the arrows. And here, each of the solid line are actually the original method. So basically the prediction method. And the corresponding dashed line shows the results of our, the one that modified by our, by doing the post-processing with our KKT. So firstly, we can see that from each of the methods, KKT can improve the accuracy by around like 1 order of magnitude. So that means we can even like get much better accuracy than the state-of-the-art method. So that is the no tears. And meanwhile, for the time it spends, we can see the dashed line is actually very close to the solid line. That means our this KKT formulation is actually very, very efficient. It doesn't add much time into the original optimization method, but it just gives a kind of a great improvement of the accuracy. So yeah, so that's the, sorry, I go a little bit over time. So now maybe I'm also going to introduce our second method. So the second method, we try to kind of take a step further from the, modify the constraint optimization formulation. So we start to think, well, why don't we just remove the constraint, right? I don't know what is your guys' like favorite method when you are, or the most impressive method when you are doing your PhD. To me, I think the one of the most impressive method or impressive solver I have learned when doing PhD is the pressure projection method for Navier-Stokes. Yeah, thanks George for introducing that to me. So yeah, one of the one of the reasons is, of course, that's a very classical method to Navier-Stokes, but also that's actually the, one of the base method for our for Nectar. So yeah, a great software. So so basically for this work, what we are trying to do is we try to borrow the idea from the projection method for Navier-Stokes and then try to apply that for the DAX structure learning. So how do we do that? Let's try to think back about the projection method in Navier-Stokes. So what it's really happening there is, well, you try to, for each time step, you try to update the velocity first. And then the next step, so basically when solving for pressure, what we are really trying to do is we project the velocity we learned into the divergence-free space. So that means instead of trying to solve the constraint optimization method problem, like using augmented Lagrangian method, like in no tears, what the projection method is trying to do is, well, let's get some approximation and then project our solution directly into the feasible space. So that's the idea we wanna borrow here. It kind of inspired us here. So to see that, firstly, let's rethink about the DAC space. What does the acyclic really physically means? So one of the classical results is a cyclic, any DAC can be associated with a topological ordering for its nodes. So that means, for example, here we have 4 nodes, like we can find an ordering of those nodes. We can find, like, say, the node 4 is pointing to node 1, and the node 3 is pointing to 1 and 2, and the 2 is kind of the basically the most offspring node. So then this topological ordering can be associated with a function, a potential function on the nodes. So for example, we can assign a potential function to be so basically the value of node J is larger than the value of node I as far as there is a directed edge from node I to node J. So here is one example here. We can associate this topological ordering with the sequence of a potential function on those nodes. So that reminds me one thing I learned in fluid mechanics. I know I was not good in fluid mechanics, but now I start to appreciate that more and more. And yeah, so thanks to George, I really learned a lot. So so in fluid mechanics, then so basically we can see that the fluid might come from the source and then flow into the sink. So we can have an analog here. We can see node 3 and node 4 as the source of the information, and the node 2 as the sink of the information. So then it can also remind me about the Hodge decomposition. So Hodge decomposition was kind of the basis for the pressure projection method. It really tells us any vector field can be decomposed into 3 components: a curve-free component, a divergence-free component, and a harmonic component, which is both curve-free and divergence-free. So then if you try to zoom in, try to kind of see like visually what does curve-free and divergence-free means. Curve-free means, well, each information is actually flowing from the source to the sink, and there's no cycle. And the divergence-free, you can see, is actually full of the cycle, full of the vortices. So therefore, this kind of visualization kind of inspired us that, well, what is the DAC? DAC means there's no cycles, right? So who has no cycle? This curve-free component. So maybe we should associate DAC with a curve-free component or a curve-free graph. So yeah, so that is basically the motivation here. So we try to reformulate the DAC space firstly into a curve-free gradient flow space. So what we are really trying to show here is, well, given any function p, so which is a function that with value on the nodes of the graph, which can be seen as like analog to the u here, then the gradient of p is actually we firstly show that the gradient of p is actually naturally a DAC. And even better, if we try to take the Hadamard product of this gradient with any skew symmetric matrix, it will still be a DAC. So that means any Hadamard product of the skew symmetric W and the gradient of P will actually be a DAC, belongs to the DAC space. And vice versa, that also holds true. We can also show that given any DAC, then we can find an associated skew symmetric matrix and the potential function P, such that, well, such that this DAC, this adjacency matrix, can be written into such a formulation. So these two spaces, they are actually equivalent. So thanks to this property, we can do the following. Instead of solving for the adjacency matrix in the constraint optimization problem, we can solve for W and P instead. So by doing that, because we know this special formulation will actually definitely give us a DAC and it represents all the DAC, we can fully remove the constraint. There is no constraint anymore if we only solve for W and P. And then we can actually resemble the matrix A from W and P once we got the answer. But however, this problem is non-convex. So like node tiers, it suffers from the optimization properties. So therefore, here comes the projection method. So then we get the inspiration from the projection method to modify that. So for the pressure projection, how do we get the pressure projection method? So basically, what we can do is we can try to take a divergence on the both end sides, and then we can get basically a Laplacian function for the pressure P and solve for that. So here we are trying to get the curve-free component. So the idea is similar. We take a divergence on both end sides, and then we can get a Laplacian equation for the U. So now we can solve for the U by the pseudo inverse of this gradient of the Cassi. So then U will actually give us, so the gradient of U will actually give us the curve-free component. So that's exactly what we do. So if we are given a matrix and any graph, any approximated graph A, which doesn't have to be a DAC, then we take the divergence of that and take a pseudo inverse of the Laplacian. And by doing that, we can get an approximation, which is in the DAG space, but which is also the approximation of the original weighted adjacency matrix. So, and we can further show that if our original weighted adjacency matrix is a DAG, then it's guaranteed that by this way, what we project to will be itself. So this can be really seen as a projection method in the L2 sense. So then by doing that, we can make our no-curl also we can make it a prediction projection method. So firstly, we can use any method. So for example, like a penalty method to get some approximation of the weighted adjacency matrix. So that means only solving the unconstrained optimization problem once, and then we run this projection. So then finally so that means instead of like in no tears or like no fears, we need to solve the unconstrained optimization problem like many times, like tens or like hundreds of times. So here we only need to solve for the unconstrained optimization problem twice. So that greatly accelerates the learning.
How do you solve the second step? Do you use method passing? How do you do these operators, the differential operators on a graph, right? You have to do it on a graph or not?
Yeah. So yeah, although it's a graph, but our graph is actually characterized by the matrix. So what we are really solving is the matrix. So yeah, so here actually we can write out this. So basically we can write out the matrix associated with this inverse Laplacian. So then by doing that, so basically this is actually, and also because we are solving the P, right? P is associated with the values on the nodes. So this is only an M by M matrix. We can write it out.
I see.
So it's like when we do the discretization method in PDEs. So this is basically the discretized Laplacian, like associated with each nodes.
Yeah.
Thanks. That's a great question. So yeah, so now maybe let's try to see again the comparison with our baseline methods. So we have so basically we have the different types of the graph. So here, for example, ER6 is very dense, and also that's the most challenging one. So the red one is still our baseline. So that's the no tears. We can see comparing with other baseline, it has the best accuracy. So the green and the blue are our method, are no curl. So we can see that, well, in such a dense and also very large graph, we get better accuracy than no tears, possibly because when the graph becomes dense, then the optimization issue in no tears becomes even more severe. So the accuracy actually got impacted. But however, also for the computational time, it's even better. So here for the second row, we show the computational time. We can see that, well, we are on par with the fastest method, and also we are like 1 or 2 orders of magnitude faster than the no tears. So yeah, so maybe I'm not going to run into the DAG-GNN, but I will directly show you. Yeah, if you're interested you can send me an email and I can like share the paper and explain to you. But maybe let me show, because I promised to talk about the knowledge graph. So now let's try to see if we apply our no curl plus DAG-GNN on the graph, on the knowledge graph. What do we learn? So for here, what we are trying to learn is the relation between edge. So that means if one relation can induce another relation. So the reason why we are doing that is by doing so, we can actually narrow the searching in the knowledge graph. So that means, well, if we already know Elizabeth has a son, then I mean, we can try to search, well, who is her spouse? So that can save us lots of time. So now here are some of the high confidence relation we learned from the knowledge graph. So for example, if we know the film is produced by, like say, whom or produced by which company, then we can actually use that to infer what is the film, what is the country of the film. Or if we know somebody's place of birth, then that's highly associated with somebody's the language this person is speaking. So yeah, so we can see that all those knowledge graph results we learned is actually kind of intuitively make sense. So okay, yeah. So because I'm running out of time, I'm going to just stop in the conclusion page, and yeah. So any question will be highly appreciated.
Thank you very much, Yueyu. This we need another hour to go through all the details of the GNN, but it was very good, very clear.
Yeah. So sorry,
we spent a little too much time on the royal family. We don't need that.
Yeah. I was hoping to let you guys see that well, this is really important. Maybe I shouldn't use the royal family. I should use the Kyriakos family.
No.
Are there questions for Yue?
Menja, do you have any questions? Menja is doing graphs. Maybe not.
Hi, Dr. Yu. Can I ask a question?
Oh, hello. Yeah. Please.
Hi, this is Jun. I have a question regarding the source-free field that you showed in the previous slides. So if I remember, no, I mean the way you use the gradient of P composed with the ReLU and the W to parameterize the source-free field.
Yeah. This one, right?
Yes. So I'm wondering this is this kind of this kind of architecture could be expressive enough to represent the general source-free field, or it is just basically is there theoretical guarantee that this can be expressive enough to represent the general source-free field? And I ask this question because I recently read a paper that I can send in the chat, which
please.
to claim that they can they design a network to learn to have the universal approximation property to learn the source-free dynamics. So just want to know if that is important specifically for this kind of problem, or you don't, or expressivity is not important in this case.
Yeah, that's a great question. Yeah, although here we are also talking about the expressivity, but the expressivity is maybe a little bit different from the source-free, because our expressivity is what we are really caring is if this structure can represent all the DAGs. So that means, so that's what we are really trying to prove in these two theories. So that means, well, any DAG can be expressed in such a structure and vice versa. So that means, well, any say linear Bayesian network can be expressed in this architecture. So for the source-free architecture, I think what you are because for the curl-free component, it has a source. It's actually corresponding to this one. So it's really not a source-free component. But I think maybe the source-free you refer to is the divergence-free component. Right.
Yes.
So So for that one, to be honest, I probably need to see the formulation first. Yeah. We are not. So the divergence free is basically the part that we want to throw away here.
I see. Yeah. Thanks.
Yeah. But that's a great question. So and I think although we don't have the expressivity issue, to be honest, we have the identifiability issue, which I didn't try to mention here, because here you can see this function, this potential function is not unique. I can also make, for example, P2 equal to 4, and that will do the same property here. So that will do the same thing. So that is another reason why that makes our direct learning, direct optimization so challenging. It's not identifiable.
Are you done, Jen?
Yeah.
Okay. These are all static graphs, right? We can do the same thing for let's say we have temporally evolving graphs. We can do the same thing.
Yeah. We also have a work on the dynamic evolving graph. Yeah, you can do the same thing for the evolving graph. And for the evolving graph, actually, you can try to like say, you can try to perturb some of the nodes. So for example, when you do the experiments, right? So for example, you can add some chemical into the experiments, so then perturb some of the nodes during this dynamic change. So basically,
Right.
yeah, so we can also model that.
This is exactly what I was thinking. Let's say trying to mimic the master kinetic equation, and you're doing reactions, and then some of the species appear, some disappear. What you're doing, you pruning, you're pruning the network, right? But but this will be nonlinear. This will be nonlinear interactions.
Right.
It's okay to handle. You can handle nonlinear interactions.
Yeah, right. That's exactly what GNN was trying to do. But yeah, sorry, I didn't have time to introduce that. So GNN is actually a nonlinear structure. I mean, handles nonlinear mapping. It even handles, for example, like different data types. For example, like discrete data, it can also handle. Yeah, we do have a paper which is still under review in ICML for the dynamic DAG learning. So that's why I didn't cover it here. And we didn't combine that with GNN yet. So that might be an interesting direction. If you're interested in, I can send you a draft. So but it's just still.
Jen is actually looking at Jen Zhang, who asked you the question. He's looking at interacting particles. So of course this would be dynamic graphs, but
right. Yeah, that's what we did for the dynamic graph, combining the continuous DAG learning actually.
But in that case, do we need the DAGs? It don't have to be DAGs, right? For interacting particles, Jen, right?
No, for that one, I just consider like undirected graph. So.
Yeah, I see. Yeah, actually, yeah, that one maybe you don't. Yeah, so that one maybe you can directly use something like a GNN. You don't.
Also, I have a question now. Now I just thought about because of the horizon that we use in this type of interactions. Can you use clicks in these graphs to reduce the cost? You know what a click is? It's like a neighborhood.
I know what click. So so basically you mean for the click, do you mean basically something like the classical one, like the two click?
Yeah, because you don't have the dimensionality of the graph is basically much weaker if you identify that you have these subgroups, right? Basically you explore local interactions and then weaker global interactions. So that's one way. The other one is I was thinking maybe what people are doing in node to vec, where they do like they balance local and global interactions by doing probabilistic walks around the to see what is the hop, how far is the hop. But it's all these it's sort of the same ideas that you have in dynamics that you know is the horizon, the interactions, right?
Yeah.
So would that make it more cost efficient? Because I could see the cost was growing fast.
Yeah, I think so. Yeah, I think that's actually really doable. And actually, I was thinking that basically, for example, the graph projection method we developed here can also be applied to something like paradynamics. Although here we handle the curve-free, right? So because for this application, the curve-free matters. But for example, if you want to handle something like maybe conservation law, like a mass conservation law, then that should be divergence-free. So therefore, we can do the projection to the other component to do divergence free.
Yeah, more like kinetics. It would be interesting actually. Kinetics is difficult. A massive kinetic equation. Yeah. Any other questions for you?
Yeah, and also I want to add maybe another thing related with Jen's work. Is another application that people use a lot for the DAG learning is trying to learn the kind of the pathway for between different chemical components.
Yeah.
So maybe that can also be applicable with Jen's work.
Yeah, the pathway and the causal effects.
Yeah, right.
Thank you, Yue. We have to call you back and tell us a little more because some data has to go to the next session. But thank you very much.
Thanks. Thanks a lot. Thanks a lot, Sandata and George.
So we'll move to our second speaker. He was online. Yeah, okay. You are muted. Dr. Kyriakos, you're muted.
Yes. Hello, everybody. I really enjoyed actually the talk I was observing, so I found lots of interesting things. So thank you.
So I'll just quickly introduce you to our group members,
Sure,
and then maybe you would want to begin. So our second speaker is Dr. Kyriakos Vamvoudakis. So he's an assistant professor at the School of Aerospace Engineering at Georgia Institute of Technology. He hails from Athens, Greece, and he has received his master's and PhD in electrical engineering in 2008 and 2011, respectively. He is currently a recipient of the 2019 ARO YIP Award, the 2018 NSF Career Award, and the 2021 GD Chapter Sigma 11 Young Faculty Award, and several international awards. And without any further ado, let's welcome him for a seminar here. You may want to share your screen, Professor.
Oh, yes. Thank you very much, Sundata. So thank you for inviting me. And it's also great to see George. So George, thank you very much for giving me this opportunity. So I saw that they pronounced almost perfectly my last name. I think it's probably because of George. So great work. So let me share my screen. Okay, so let's see if we can see my full screen. Can you see my full screen?
Yeah.
Perfect. Okay. So, so today I will talk about learning-based actuator placement and allocation for resilience against attacks. So for a minute, I always think that my presentations are too mathematics, but in this group, I will not have a problem. So, okay, so the outlines, of course, I will motivate why we want to work on this project and why we want to work on these problems. What is the underlying idea? So I will describe different ways where you can guarantee security, you can learn where to place your actuators, and you can allocate actuating power in real time. So you will see lots of cool theorems in math and lots of learning ideas. So hopefully this talk will also bring some collaboration. So yeah, so this is my outline. I don't want to bore you more because you will see that more. Our work actually tries to bring ideas from AI, reinforcement learning, in a feedback loop, learning-based control, in other words. And we try to bring ideas to cyber-physical systems. So what we want to do is our work goes from controlling, resilience, detection of attacks, and so on and so forth. So of course, cyber-physical systems are everywhere, and this interaction between the cyber part and the physical part. And so I always say that cyber-physical systems, it's a way of a multi-agent system. It's pretty similar to what also you saw with all these interactions, and then you can describe interactions with a graph, and then so on and so forth. Okay, of course, since I'm in aerospace engineering department, although my background is electrical, I have to always show pictures of plane. Okay, so again, why we want to work on this domain is because, of course, our lives depend on them. Of course, I'm sure you saw that cyber-physical systems can be considered everywhere, from power systems, healthcare, and so on and so forth. Okay, of course, one part that we are interested in is how to secure this, how to develop these learning-based controllers with the beauty of feedback that can guarantee that we can control the system in a resilience manner. Of course, there's lots of things that have happened during several cyber-physical attacks, and the most famous is Stuxnet, of course. German Steel also, German Steel meltdown was also another thing, and so on and so forth. Okay, so now, of course, let's go to the meat. Okay, so the first idea that I will describe is how we can develop receding horizon control for security against stealthy attacks. So what is stealthy here? Stealthy is when I have an attacker, and the attacker will give me the same output of the unattacked system, and the attack system will be the same. Okay, let's see what we have. So, of course, attacks, they vary in types. So we have sensor attacks where I change my sensors. I have actuator attacks where I introduce faulty control inputs. I have denial of service attacks, which of course in cyber-physical systems, you jump the connection between the plant, the sensors, and the plant and the actuator, or the network and the sensor and network, the actuators. And the stealthy attacks, which are actually one very interesting thing in cyber-physical systems, because most attacks are stealthy attacks. They're the attacks that they cannot be detected. And so let's see how everything appears in this diagram. So we have the system. So we want to deploy detection, and we want to do state estimation, and we have some actuator attacks. And of course, if you have just actuator attacks, this will lead to some unsafe regions in the state space. And of course, this is harder when I have uncertainty into the system. So of course, uncertainty, I mean, I never really know the plane dynamics, or I never really can measure the disturbance or anything like that. So the attacker can hide inside this uncertainty. And based on this uncertainty, we don't know he is there. And then he can create problems in our system. You will see how this works. Okay, so this can potentially, by being stealthy, it can give us the wrong state. If, let's say, for example, instead of controlling the system, we just want to do state estimation. So I want to estimate the state of my system. Okay, so how can I mitigate these scenarios though? So game theory is one idea. Of course, it considers worst case scenarios, and we use equilibrium-based concepts. Another idea is to use receding horizon control, where I devise stable and optimal control laws, so for different time steps, and then I predict in the future. And of course, the beauty about receding horizon control is I allow constraints that characterize stealthy attacks. So one constraint that you can see is that output of the attacked and the unattacked system, they are the same. So I want this message to be clear to you. Okay. So of course, if I combine the game theory receive horizon control, then I can see what I can do and eventually estimate securely my state even in the presence of attacks. Okay. So again, we will combine ideas from game theory and receding horizon control. We will develop a moving horizon estimation technique that can estimate the state even in the presence of stealthy attacks. Okay, so now let's start working on some math. Okay, so first, system controls people. What we start first, of course, we'll start with some dynamical equations. Okay, and so you can see that the U, which I mean, we can call it either control, but in this scenario, let's say I will call it a defender input, okay? Because again, I want this control to make me estimate the initial conditions. So again, a state estimation is based on output measurements. I want to estimate my state, okay? So in other words, somehow like building an observer. Okay, so I have the attacker's input, okay? And then I have a disturbance, okay? And I will give a slight advantage to the attacker, because usually all these things, whenever we develop mitigation strategies for cyber-physical systems, we will assume that the attacker always has more knowledge than the defender. So now, let's say I have this disturbance, which appears in this little green, and then the attacker.
Kyriakos, can I ask a question on the setup? What's the difference between a disturbance and the attacker's input? Isn't the same thing, or? Okay, so you can consider because you add them up. It seems that you add them up, so it's exactly. You have to have the same unit. It must be physically the same thing. Yes, it's physically the same thing. So, for example, let's say you fly in a plane, and then you have a wind gust. Okay, but the wind gust also can create. Also, you have an attacker input who will actually manipulate you, and then he hides inside the wind gust. So that's why I want to differentiate them for now. You will see why. But it's definitely the same thing in the system. So you can always treat them as one. And your model also has to be linear, or just for the sake of just for the sake of presentation. Okay. Yes. Okay. So now we have the U, the D, and the A, and I have my output, of course. Okay, which is of course everybody can measure the output. Okay. Now let's start with some assumptions. So of course, in order for me to develop some strategies, the disturbance has to have a known bound, right? And then in order for me to guarantee stealthiness, I will consider an attack-free systems. You will see now that is why I differentiate A and D, because I want to consider attack-free dynamics. So where I can have my control input U and my DH, which is the disturbance, but it's not known by the U. The disturbance is only known by the attacker.
Okay, so eventually I want these two systems, the plant dynamics of my actual system and the attack-free dynamics, I want them y equals to y8. Okay, so I want the attacker to put the input A such that eventually what the defender sees is y equals y8. Okay, and he can do that only by hiding under this bound of a disturbance. So let's see how we can do that. Okay, again, the attacker's goals, we want to achieve stealthiness, and I want to deteriorate the plant's performance. Okay, the defender's goal, of course, I want to estimate. Okay, or I want to estimate it for some basic condition, or I want to regulate the system optimally. Okay, so if, let's say, in the extreme scenario that the attacker is not that smart and he doesn't want to hide, okay, so of course, a non-stealthy attack, I can use some intrusion detection, and then I can stop the process. Bam, ready. So the stealthy attacks, let's see how we can deal with those. Okay, so again, as I told you, we will use game theoretic and receding horizon control along with state estimation. So what we want to do is we want to estimate a worst case initial condition based only on output history. I want to predict the worst case stealthy attacks using the attack-free model. And then I want to control my system by computing the zero-sum Nash equilibrium. Okay, so the first two blocks, they lead to safe mitigation policies, and the last block, that's my control allocation for secure stabilization. So of course, we have to guarantee lots of beautiful properties you will see soon. This includes robustness, stability, etc. Okay, so now, again, I want to do that. State estimation only collects data, okay, data from the output. Based on this data from the output, I want to estimate my initial condition, okay? So of course, I can collect data only in the past, right? I cannot really collect data in the future. So now what I have, again, let's recap again. So I have this system. This is actually the system that the attacker and the defender will take care of. And my output, you'll see that it's measured only in the past. Okay, let's see how this can work. Receding horizon control, though, as you remember, I am in TJ and I go to the future. Okay, so what we have to do here, okay, because the measurements from the state, from the output that I have, they are of course in the past. I cannot, for example, measure a sensor in the future. This doesn't even make any sense. Receding horizon control works in the future. So let's see how we can mitigate that. One, the easiest thing we can do is reverse this past model, right? So what I will do is I will rewrite this reverse past model, which can be derived like that, okay? Again, this is just by simple calculations. And then I can eventually provide that I can still get my two states are the same, given that this condition is true, okay? The one that hopefully you can see with my mouse.
Hey,
okay.
This is Adar from Brown. Can I ask a question, please?
Sure.
From my experience with time reversal based message or reverse time regression, the dynamics have to be time reversible. So, for example, like wave equation, it is time reversible, but the heat equation is not. So you assume the underlying assumption is that your system is time reversible.
Yeah, this is an ODE, this is not a BDE. So yeah, it's you can consider as time reversible. Yeah.
Okay, thanks.
Okay, so now let's start defining the optimization. So what I will do is I will define game theoretic receding horizon control from both sides. One side from the defender side and one side from the attacker side. Okay, so now what we have is, of course, when you do this type of optimization, of course, you have to penalize your state, penalize your control input, okay? So as controls people, we want to minimize our control. So I will call ourselves pessimists, while the people that want to make some money, they're more optimists, right? So that's why, because the attacker, I guess he wants to make money, so that's why it comes with a minus there. So that's why you do a min and a max. And then, of course, this will run forever, ideally. So we have to actually change this cost and incorporate the final condition, which actually is needed for stability, as you will see later. Now, this has actually become very tricky optimization problem because I have dynamic constraints, which they're listed here, because they have to do with the future, the past, and the future attack free. And then I have path constraints, and then I have boundary constraints. Okay, so I don't want to bother you with all these things, but this is all the constraints that you can consider in this problem. Okay, so again, we have the dynamic, the path, and the boundary. So the output compatibility, remember, is for stealthiness. Okay, so this is a constraint that we want to force such that the attacker doesn't get detected, because then it becomes too easy. Okay, and of course we have to incorporate some other ones that are because of worst case state estimation. So all these things there to make sure that the problem is feasible and the problem has the required solution. Okay, so now to answer George's comment also in the beginning. So here you see that I maximize over the whole space of the combined disturbance and attack, because the attacker and the disturbance can be considered as one is optimization, because the attacker knows the disturbance, but the defender doesn't know. Okay, so one problem that we can see here is that the cost is not really concave with respect to maximizers. Okay, so what we can do is I will try to concavificate this cost. Okay, so I will just try to relax it. Okay, so I will do some manipulations and I will do some induced concave terms for the problem to actually be concave with respect to the maximizer. And then I will see, okay, how far I am from my reasonable gain. So approaches the reasonable gain as all the induced term weights, they go to 0. And of course, I can do that by picking the appropriate cost user-defined matrices in this penalization. Okay, so of course I can enforce my path constraints and all these things. Okay, again, same things, and then I can finally have my theorem. Okay, so this is from the defender side. Okay, so the NAS controller or the defender is given by this. Okay, and all these other things, they are the cost states that they are derived from the minimax optimization. Again, all these things, they look kind of messy, but it's simple optimization based on Lagranges. Okay, so this is the NAS defender's policy. Okay, let's see what happens from the attacker side. Okay, again, the attacker's point of view, the attacker wants to hold stealthiness. Okay, this is the constraint he wants. He wants to hold stealthiness and then do the maximum damage by deteriorating the performance of our system under control. Okay, so again, we can see that the attacker can remain detecting over the interval. This one by enforcing this constraint here, which again is for stealthiness. And then you can see that I can also have some more dynamical constraints, which are pretty similar with before. But again, I don't really know. That's why you see this UA here, because I don't really know what the defender will do. So he assumes that the UA will do something and this will follow another trajectory. Okay. Again, this is the knowledge of disturbance for the attacker, because he wants to remain stealthy. Okay, and then this is what I just told you. This is not the actual defender input. Okay. Now, again, same things. Okay, so this is done by the attacker's optimization. This is a concavification term, and then I have similar constraints. I have the nominal model, the attack-free model, and then I have the disturbances that are bounded by delta, and I have the boundary conditions, and then by enforcing these things on the orange, I can guarantee constraints. Okay.
Kyriakos, can I ask you, where is the from the defender in this equation? Where is the defender terms?
Oh, so the defender term here, again, we don't really know. This is again the attacker side. So
right,
attacker,
I know, yeah.
So this UA, okay, is the potential actions of the defender.
Oh, I see. But
so
there's no measurement.
What he's doing.
There's no measurement. The UA will be the measurement.
Oh, UA is a potential action. I don't measure anything. I can measure only the output here.
Yeah. Okay, so but I need to know through imaging or some sensing. I need to know some trajectories, some part of the trajectories of the defender, right? Otherwise,
yes. I observe. I know the nominal model. I can measure my state. Okay, but I don't know how the actions took my state from where I was to where.
So X. So you know something about X then? X.
Yes.
Okay.
Yes.
Sure.
Okay. So now. Again, same things with before, but now from the attacker side, okay? So this is the NAS controller for the attacker. And these are, again, the cost states, okay? So Of course, since we are controls people, we like everything to be bounded, okay? So remember I told you in the beginning that I have to incorporate a terminal cost to guarantee some properties of stability. So then I can eventually guarantee that all the closed trajectories are bounded for sufficiently large weighting matrices or maximizer. And it's of course sufficiently small control horizon. Okay, so everything for now, we have developed the worst case defending strategies by solving an optimization from the defender side. We have found the best case attacking strategies by solving the optimization on the attacker side. So I know what everybody can do in the worst case. Okay, so let's see now how we can take it one step further. Okay, now let's say that I don't want only to estimate my initial condition, but I want to do something more. Okay, so what I want to do is I want eventually to place some actuators, okay, and while the attackers are trying to make me place the actuators in the wrong places, but again, they want to remain static. Okay, so what I want to do is I want to design this control system now that involves the selection of each actuators. Okay, of course, whenever I pick the actuators, I have always to optimize controllability. Okay, and of course, since I care about cost, I cannot really include like 1 million actuators because then the problem will be infeasible to even place them. Okay, okay, so same things. So now I think you will see some connections to learning. And okay, so what I want to do now is I'm vulnerable to these actuation attacks. Okay, my dynamics are unknown. Okay, and I want to learn in real time how to place these actuators while at the same time I have stealthy attacks. Now, again, we have similar things. Okay, now though, I will, as also Joe suggests, I will take my A and my D to B1. Okay, so again, same thing with before. Again, all these things that we do, they actually can be generalized to nonlinear systems. This is just for simplicity. So what I have here, again, I have the A, I have the B, and so on and so forth. And what I want to do is I want to play with some components of the B. Okay, so let's say I have a large-scale cyber-physical system, and then I start with some actuators already incorporated in the system. So these actuators I cannot really move. Okay, and then inside this B matrix, I have some parts that I can change. Okay, so the parts that they cannot be changed are this B0, and the parts that they can be changed are this BV. Okay, so again, I want to learn in real time by using reinforcement learning without knowing the model. For example, here you can see that I won't be able to know A and B, for example, here. I want to place the BV, which by placing the V1, V2, and so on and so forth. Okay. Now, this actually is if I didn't want to employ learning. So in order for me to play with this V, okay, so what I want, the problem I have is I want to choose a set of actuators. Okay, so remember I have V1 up to VK. So here I have again, I pick this V1 up to VK. So what I want to do is I want to maximize a metric such that the cardinality stays the same. Okay, and of course A is uncertain. Okay, okay. Again, when now I design this optimization, remember that every time I place my actuators, I have to guarantee that controllability is there, right? So I have to optimize a form of controllability, but in the same time, I have to incorporate that when I place my actuators, even in the place of attacks, in the presence of attacks, I'm resilient to them, okay? And of course, I mean, one small actually thing that we need to know from the A for these specific scenarios is that I need to know an upper bound of the spectral abscissa of A, but nothing else. Okay, so the first problem that I want to consider here is I want to find a metric that quantifies both controllability and actuation attack resilience. Okay, of course, I want to do that in a tractable manner because I don't want to place the actuators in infinite time. And usually all these things, they converge in infinite time or they're computationally feasible. Okay. And even on top of that, if I don't know the model, things are even more tough. Okay. So let's see. Now, since A is not known, okay, the metric of controllability needs to be estimated. Okay, so I cannot really just solve the optimization problem offline and then take the input and then put it, because I have the constraint that I don't really know the A metrics. Or as you consider, it's I know only, as I said here, an upper bound of the spectral adhesion. Okay, so the problem 2 will be I want to estimate my F. Okay, and then problem 3, as I told you, I want to make everything in an efficient and guaranteed way to converge to the optimal set of actuators. Okay, now what you will see here, I will reframe everything with respect to problem 3. Okay, so again, problem 3. I mean, I can place my actuators only in specific times, right? I mean, I cannot really move actuators every milliseconds because it's expensive, or it doesn't even make sense because I don't even have time to control my system. So what I will do now is I will redefine my state space that you saw before, okay, to take care of the definition of what I want to solve for problem 3. Okay. So now I have this new state, which is X bar, okay, and then I have this this time varying B, where I have my B0 and my BVJ, but of course everything the variation of B, okay, happens for all t inside this interval. Okay, now let's go back to our favorite games. Okay, so what I want to do is now I want to solve a constrained zero-sum game. Okay. So as you can see here, every time I define a metric like that, this is a classical control metric where, for example, if you didn't have the A, right, and then instead of this case, you have X transpose Q X, you're going to penalize the state, you're going to penalize the control, so then it goes back to classical QR linear quadratic regulators, and so on and so forth. So now, as you see here, what I have is I have this U transpose RU minus A transpose KAT. Okay, so again, it's a minimax problem, right? Given the equality constraints that come from dynamics, initial conditions, and the final conditions. So what the defender wants to do, wants to regulate the system with minimum energy because it's the minimizer. Okay, as I told you, we're like pessimists. The attacker from the other side, he wants to disrupt this regulation. Okay, and of course, the R and the V, they depend on how you pick your actuators. Okay, so they're also time varying. So this is my problem for now. So of course, we have to get some guaranteed assumptions to work, right? So I mean, the system is controllable, and my case greater than R. Then I have a saddle point solution, okay, and I can find actually what is the saddle point solution. And then this Q that you see here is the controllability graph, okay? So we will call it for now robust controllability Gramian, because remember, I have also incorporated this resilience from the attacker side. Okay, so if I had, let's say, information about all the systems, right, I can take care and I can solve it offline, and then I can guarantee all the beautiful properties, okay? And then eventually, I can uniquely solve this equation, which is a classical Lyapunov equation, okay? But again, this requires the model. Let's see how this can work when we don't require the model. So what we wanted to do is, before we go to the learning-based components, what we wanted to do is we wanted to have something to compare with. So this is the offline model-based technique, and then in a bit, we will compare it with the model-free learning-based technique. Okay, so now let's start working on going from problem 3 and going back to problem 2, problem 1. Okay, and then eventually after I go to problem 1, then I have to solve all the problems. Okay, so now to minimize this average robust controllability, right? So remember that this F was a controllability metric. So what I will do, I will just define this F to be the trace of the controllability grammar that you saw before. Okay. And then this is again easy to solve. I can find the unique solution of this dual Lyapunov equation. Okay, and of course, this means that only one Lyapunov equation needs to be solved to evaluate this metric F. Okay. Second advantage of this metric is that it can be optimized in polynomial time. Okay, and of course, we can reduce all the complexity. Okay, and then we can play with some matrices, and eventually, I can find that given now that the state matrix is uncertain, I want to find the optimal set of actuators. such that we solve this optimization problem. Okay. Okay. So now let's start going into learning. So every time we do reinforcement learning based control, we have to guarantee that our system has rich inputs, right? So of course, this goes back to exploration, exploitation, and all these things. So in optimal adaptive control or reinforcement learning based control, this is similar. This is what is called Bayesian excitation. Okay, so this is nothing more than making that some systems are they have rich inputs. Okay, and then you explore the state space efficiently. But everything goes down to this inequality. Okay, so now let's start building the learning now. Okay, so again, I have the state trajectory text bar that you saw before, and in the absence of attacks. Okay, so the database time-dependent equation can be defined like that. So the vector right is a vectorized form of the p gamma. So before, of course, p gamma is unknown. So what I will do is I will define a vector. I will define some unknown weights there. Okay, so and then after that, okay, so I can guarantee that given this psi is persistently exciting, I can learn the solution in a completely data-free way. So as you see here, okay, I don't require any information about the system. Okay, now let's start doing how I can actually update these weights. Okay, of course, I want to learn my weights, and then in order for me to update them, I have to define. So you can think that I vectorize all the weights of p gamma, and then since they're optimal, of course, I don't know them, so I have this p gamma hat. Okay, so I want to minimize this error that you see, this performance, which is equal to 1/2 e squared. Okay, so where e, this error, you can call it temporal difference error, is the data-based Lyapunov error. Okay, so of course, if this is 0, if error is 0, then actually I can solve my Lyapunov equation. Okay, so what I want to do is I want to find a tuning law for the unknown weights, which in this case are the vectorized forms of this p gamma hat. Okay, again, as you see here, I want the easiest way to come is just use some gradient descent learning laws. Okay, and again, by plugging and play this learning rule, okay, where you can see some normalization here happens just for stability purposes, and also to enhance convergence. So by plugging and play this gradient descent learning law, I can eventually learn the optimal allocation. You will see how you will look in simulations pretty soon. Okay, of course, I want to prove that everything is correct, right? So we always want to prove boundedness or asymptotic stability. So this p gamma is the difference of the optimal and the estimated ones. Of course, in order for me to guarantee convergence to the optimal solution, I have to make sure that either this goes as that this is very close to 0 if 0 is 0, or very close to 0 if 0 is almost difficult to prove. Okay. And so what we will do is that this gradient descent law guarantees that this estimation error vector that you saw before is non-increasing with respect to time. And then if my system has rich enough inputs, which goes back to persistent excitation, so then I can guarantee that the norm of the estimation error vector decays to 0 exponentially fast. Okay. And again, this just a simplification in the presentation. Trust me, the proof is very, very long for these things. Okay, so now, having an estimate of this p gamma, we can solve the approximate optimization of what you saw in the beginning, right? So you remember I had f, but now, because I don't really know f, I have f hat, because I have put p gamma hat there, okay? So now, I have actually reduced my complexity a little bit, okay? And now the complexity is n log n. Okay, so this is the database actuator placement. Okay, this happens in real time. Okay, so what we do, we start. We want to select the actuators. Okay, so we learn the p gamma. Okay, what we do then, we do approximate optimization, and then we switch actuators, and then we optimally place them. Okay, so all these things, they happen in real time. And then, given that the optimal set of actuators is unique, it can be found and scheduled in finite time. So this actually uniqueness assumption can be realized by using a quantified suboptimality. And This can be done in different ways, okay? So of course, this can be some independent random variables, and then this can help us solve this assumption. Okay, so then again, we have also proofs given to the perturb system. So I can see a typo there, but still the perturbs admits a unique solution with probability 1, and it holds that the estimate of what of the optimal metric versus what I computed is very, very small. Okay, so as I said, remember that in the steady state of the learning law, I can also detect actuation attacks that they can happen in a partially modeled free way. So what I mean by that is that, let's say that the attacker doesn't want to be stealthy, but in the steady state, I want to develop an intrusion detection mechanism. Okay, so what I will have a filter, and I would check if this gives me some erroneous measurements. Okay, so now you can see that again that the disturbance that comes to the game. So again, the disturbance can be isolated by the attacker by taking into account that while I estimate my piece, I can have some approximation errors. So the attacker can hide inside its approximation error. Okay, so and then we have some guarantees that about stealthiness, but it's similar with before. Okay, so now let's see how all this is going to work. So we have an aircraft. So again, I'm in aerospace, so I have to solve pictures of aircrafts for my department chair to be happy. So let's say that I have 8-state aircraft, which is flying at an altitude of 15,000 feet. I have 11 available actuators, and then I can pick only 4 of them. Okay, and then the optimal set of actuators, okay, is B1, B3, B7, B10. Okay, and actually this can be found offline. So let's see if our learning actually can learn this optimal set. And I remember that I can change my actuators in some intervals, and let's say that the actuators are switched every 20 seconds. Okay, and this is just some control weightings. Okay, so we have these numbers. So let's see what happens. So on the left plot, you can see that I'm able to learn, okay, this P gamma in real time. Okay, and then on the right, you can see that the Frobenius norm of the estimation error actually converges to 0. Okay, now I want to compare if my actuators that I can find offline to compare, that you see here, B1, B3, B7, B10, can actually be learned, and my actuator, my learning-based actuator, can learn this sequence. Okay, let's see. Now, since I have learned my P gamma successfully, let's see what happens to my actuator sequence. Okay, so the cyan color denotes that an actuator is chosen, while the black denotes that an action is not being used. And guess what? The cyan color is only shown us that eventually I converge to what you see here, B1, B3, B7, B10, which is actually what I converge here. Okay, and on the right, you can see also the evolution of the trace of the controllability. Okay, so and remember that I switched only, I think, let me remind myself what was the switching, every 20 seconds. So I learned everything, the optimal set, in 300 seconds. Okay, again, this is model free. I didn't require information about the A, and I was also I learned the learning based. I learned the optimal sequence of the actuators. So to the best of our knowledge, probably this is one of the first works that I can do that in such an efficient time with provable guarantees. Of course, we can also check if our detection works. Okay, so let's say that after 500 seconds, let's say if I can detect an attack. Okay, so I will deploy my detection signal, and I can see, okay, yeah, after 535 and between 535 and 565 seconds, I saw this difference in my detection signal, so I can guarantee that an attack happened. Okay, so this is almost my my second part of the talk. So let's go to the last one. Okay, so now what I want to do is I want to make the problem a little bit harder. Again, I will consider linear systems, but of course we can do nonlinear as well. So what we will do is I want to do database actuator selection, but I want to do that not only for optimal control and resilience, but for optimal control allocation. It sounds intuitive, but you will see that some major things have to be changed, even in the Riccati equations. Now, let's go back to this one. So system dynamics, okay. So X is the state, V is the specified control input, A is the unknown plan matrix, and G is the known input matrix, okay. So what I want to do is I want to map from actuators to controls, okay. So whenever you see this V, I can write as BU, okay. And then this B, it compromise the actuators of the systems, and then U contains the commands, okay. So we will call that the system is actuator redundant if its mapping from actuator commands to control input satisfies K greater than M, and the rank of B is M. Okay, some things to make it work. Okay, so now I want you to know some things here. So regarding actuator redundancy, the control input V can be designed irrespective of the actuator matrix V. Let's see why this can happen. Actually, all these things they seem easy, but there are some things that we have to consider. Okay, so example, let's say I consider the actuator command to be this U, where B is the pseudo inverse V, and then this is the range particular V with a signal Z that is an arbitrary signal. Okay, so it can be seen that I can pick this BU as follows. Okay, and then this can still give me V. Okay, so there are infinitely many ways to choose U, okay, because Z is free, okay? But what I want to do, I want to take out this infinitely many ways, and I want to choose the U with the minimum energy, okay? Again, I have infinite ways to design this U. Even again, I have these U and V's, okay? So I have actuators and control inputs, but there are infinitely ways to exist to choose this U. Okay, so what I want to do is I want to choose the U with the minimum energy. Okay, so the first thing that comes into my mind, and probably to controls people's mind, is that I want to choose this U with minimum energy. So what I will do quadratic, right? So what I will do, I will define my performance LU, I will do U transpose WU, and then my constraint will be V is equal BU, okay? And then, of course, my W is just a diagonal matrix that assigns a weight to its actuator. Okay. Of course, the optimal solution can be found pretty easy, right? This is an easy problem to solve. And I also can find the optimal cost. But I wanted to note something here. The optimal cost can be further optimized here by choosing B. Okay. So again, before, remember what I did. I chose B just to place my actuators. Now I also want to do allocation. Okay. So when I allocate and I find the best controller here, I also have the freedom to play with a B. Okay, let's see what we can do. So remember, before we did actuator selection, now we will do actuator selection for optimal control allocation. Again, I have two parts. One is the fixed part and one is the choosable part. Okay. What I want to do is I want to pick the choosable part such that the minimum energy that you saw in the beginning, I mean, a couple of slides before, is minimized. Okay. And of course, this phi B has to quantify this minimum energy. Okay. Now, I have to assume that the matrix P1 that you see as the fixed part has full row rank. Okay. Which is not a big assumption, but this assures actuator redundancy. Okay. Now, let's remind ourselves again that my cost can also be improved by picking B. Okay. So since V is not fixed or known beforehand, we cannot really directly optimize this LB over all the Bs. Okay, remember that I have again to change the Bs. Okay, but what we can do is we can optimize on average and choose F as follows. Okay, that's why you see all these beautiful traces there. But of course, this seems that it can be extremely hard to optimize. Okay. What we will do is we will try to find some simplifications, and instead of going the calculations that you see on the right hand side, we want to employ the calculation that you see on the left side. Okay, this is for simple scenarios. Again, this is just some things to show how we can pick the pairs. Okay, so now because this is very agnostic. Okay, so for any positive definite matrix E, I can show that I have this this inequality. Then instead of minimizing the trace that you saw before, we can instead relax the problem and minimize this thing over here. Okay, so the only difference that you see here is just a minus sign and not an inverse. Let's see what we can do here. Okay, so now the node, we can play with some things there. I can define some numbers. Okay, so this can be optimized by sorting, and the complexity is reduced to n log n. Let's see now what happens if I know something about my VT. Okay, so let's say that I have some knowledge about the VT and the initial condition distribution. In particular, okay, my VT, let's say it's feedback. Okay, so its feedback K is a cost, gain that can be selected by your favorite control technique, which can be, for example, like QRP addition and so forth. Of course, I want to guarantee that every time I pick my K, my eigenvalues of the closed loop system are on the level plane, or in other words, A plus G2 is square roots. Okay. Okay. So what we can do is now we can optimize the minimum energy directly over this infinite horizon and choose phi as the follows. Okay, so the f now, or phi, is given by this one. Okay, what I have done is I have substituted my u equal to kx. Nothing too smart here. Okay, and this cost actually can be written in a static form using Lyapunov equations. Okay, so this they can be solved by after some simple derivation, I can find these Lyapunov equations, which I can solve them. Okay, now I saw that all these things are equivalent. Okay, and using this trace PV that you saw before involves solving Lyapunov equations across all points in the state space. On the other hand, by using this phi of B, which is the trace of QR, requires solving a Lyapunov equation for every Q only once. Okay, so the previous course also involves the matrix that, which is very slow to solve. Okay, but we can actually get some relaxations here. So we can assume that G square in the case non-singular, and instead of this trace QR, we can say choose B to minimize this thing over here. Okay, and then I can write all these things down, and then I can have everything with respect to the subcomponents of everything. Okay, again, all these things, they can be optimized by sorting with a complexity n log n. But can we solve this optimization problem by using learning-based techniques in a model free? Let's see what we can do. So recall that the cost functions, what I have is I have the trace QR and the trace R inverse Q inverse, okay, subject to these Lyapunov equations. Now, the A matrix that you see that I want to avoid, okay, appears only in the second Lyapunov equation, okay? What I want you also to see is that this cost depends on Q, which in turn depends on A through the Lyapunov equation, okay? So, of course, through our work in reinforcement learning, we know how to solve these Lyapunov equations, model free, but if we solve this Lyapunov equation, we can also still perform model free actuator selection. Okay, but there is something here. Okay, the Lyapunov equation is not really the one that is known in controls. Okay, in other words, the Lyapunov equation above is a dual Lyapunov equation. Okay, so what this means is it doesn't really have a relaxed version that I can directly use to solve by using our techniques in reinforcement learning. So what I will do is I will turn this dual Lyapunov equation into a nominal algebraic Riccati equation. So let's say on the left, you see this dual Lyapunov equation. What I will do is I will multiply left and right with Q inverse. Okay, and of course I can do that because Q is not zero by theorem 1. And I can have what you see on the right hand side. Okay, why I can do that? Of course, in every Lyapunov equation, in every actually Riccati equation, you have multiple solutions, but you have a unique solution stabilizer your system. Okay, so instead of Qx, I just write here. Instead of Q inverse, I write X. So I don't want to make it have all these inverses. Okay, so what I want to do is I want to solve these algebraic Riccati equations in a model-free way. So in other words, I want to find a gain that stabilizes the plan, A plus GK, I mean, an optimal gain. And I can do that by using Kleiman's algorithm, which is model-free, or I can use any approximate line programming techniques or off policy. Okay, but as I told you, this algebraic Riccati equation is weird. In other words, it has no constant terms. Okay, we don't really care about the stabilizing solution here. You will see why. Okay, so the general form of the Riccati equation, you can see it's here, right? I'm sure here we're familiar with algebraic Riccati equations. The solution that I can find to this algebraic equation is called stabilizing if my closed loop is Hurwitz, okay? But the solution XA to this equation is called anti-stabilizing with respect to A if all eigenvalues of the closed loop system have strictly positive real parts. Okay, so again, I have the stabilizing solution and I have the anti-stabilizing solution. Okay, and what I want here is I want to solve X. Okay, but I care about not about the stabilizing solution here, but I care about the unstabilizing solution because remember I have this Q inverse here. Okay, and my algebraic Riccati does not have the constant terms to all these things. Okay, so let's see. So now one thing here is if we pick a stabilizing gain and do policy iteration, we will get 0. So then why do that? So let's see how we can actually mitigate this thing. So what I will do is I will re-express this algebraic Riccati equation. So while Q this inverse is not the stabilizing solution, it is convenient that it has been characterized as anti-stabilizing one. Okay. So if the A plus GQ, if this Q inverse anti-stabilizes A plus GQ, it will stabilize my minus A plus GQ. Okay.
Hi, Professor. We just wanted to remind you that we just exceeded some time. So
yes. I will. Yeah, I will actually. Yeah. So I will end up pretty soon. Yeah. So just give me 2 minutes. So and then we can learn all these things by using data-based policy iteration. Okay. We have a proof that is actually different from the conventional ones. Okay. And I can prove that the policy iterations they can converge. I can use my off-policy learning to learn everything in a database framework, okay? And instead of learning the stabilizing solution, I learn the anti-stabilizing solution. I have proofs that everything converges to the optimal solution. And finally, I can show how this can work in eVTOL, okay? So I have 9 states and 5 high-level control inputs. And my input matrix is selected as E4, E5, E6, E7, E9. Okay, so this is the set of available actuators, and the initial actuator set is given by that. Okay, so I want to augment B1 with 6 more actuators. Okay, so what I will do, I want to learn this optimal sequence. Okay, so as you can see on the left, you can see my state, you can see my V, and this is how I learn to allocate optimally. Okay. And then this is the end of my talk. So what I said, what we have discussed, we have shown how we can define game theoretic frameworks in receiving price on control, where I define my policy from the defender and the attacker. I have actually extended that to placements, and I actually also extended my placement to allocation. So there are many things we can do. Okay, so we can use different techniques of learning. We can use prior information that actually we're very interested in your group's work on physics-informed neural nets and how we can use information about the system, and then based on that use some techniques in reinforcement learning and so on and so forth. And then without my wonderful student Philippos, who is actually the person that did all this work, and he continues to impress me with all this deep technical work he does. And I want to thank you for this opportunity to talk to your wonderful people at Brown, and I'll be happy to answer any questions.
Thank you, Kyriakos. I have a question. You refer to matrix A as uncertain. It's actually unknown, right?
Yes. So why I put it uncertain? Okay, actually it's unknown, but I put it uncertain because I know this upper bound on the spectral of Skissa in the first part. In the second part, I don't know anything about it.
Yeah, because we have a small subgroup. We're looking at drones, trajectories, and so on. And I don't know if Ting Wei is here, but she. So we're trying to see like how we incorporate actually uncertainty into this side. So I was wondering if you were to put uncertainty, where physically? I mean, not we can of course mathematically we can put it anywhere we want, and we can devise a new stochastic ODE and so on. But what does it make sense to have, let's say, because the actuators, what would be uncertain here? Of course, you don't know the input from the attacker is unknown, not uncertain.
Mm-hmm.
So where I want to differentiate between maybe Ting Wei. Do you have any comments for Kyriakos' talk?
Yeah, actually, thank you for the talk. This is very interesting. Actually, I have some questions because there are several models you have for the optimal control problems. And I don't know if I understand correctly, you have the later models because you have something unknown in the matrix B. Is it true?
So, okay, so throughout our work, to also answer George's question, because I think the two are related. So we consider uncertainty in, we don't know A and B, for example. So you say you have a system and you don't know the mass, you don't know anything, you have completely black boxes in A and B. If you go to nonlinear systems, you can consider, I don't know, f of x and gx, okay? You don't know the disturbances. So what we want to do is we want to use reinforcement learning-based control to actually solve online in a model-free, what's model-free, I mean, without knowing A, B, or fx, gx, in a model-free way, and still converge to the solution if I have the model. So you can think about it as a plug-and-play model-free framework, and this is the uncertainty that we're talking about, uncertainty into the plant dynamics mostly, uncertainty in any disturbances that you have into your system, and so on and so forth. Okay. So if you have, for example, a drone, it's mostly very, very tough to even model it. So modeling a drone in a nonlinear case needs all these derivations, but we have a framework also that we don't require information about this nonlinear dynamics. Okay, so I can send you some papers anyway if you're interested. If you can send me an email, I can have your email, and then I can send you some papers that they actually devise learning strategies for completely unknown systems. And unknown, I mean A and B or fx, gx.
Okay. Thank you.
You're welcome.
And how did you use the reinforcement learning? Did you combine it with your model? Because I saw you,
So what we did is we use, again, we do everything continuous time, continuous state, and continuous actions, right? So what we did is we devised actor critics. So for example, I approximated my control with an actor network. I approximate my cost with a critic network. I define tuning laws for the weights of the actor and the critic. And then eventually I can solve, because reinforcement learning is like solving optimal control problems, right? But you solve them online. So that's the beauty of reinforcement learning. So we use this actor critic tuning laws in a plug-and-play framework without pre-training to guarantee that we converge to the optimal solution. That we can provide stability and all these guarantees.
Okay. So by saying reinforcement learning, you don't mean that you have a neural network to approximate the controller?
Yes. We have an actor, and we have an actor, which is a neural net, and we have a critic, which is a neural net to approximate. So again, we consider simple networks with the linear parameters weights. Okay, of course, you can consider with multiple bases and so on and so forth. We have considered deep neural nets and so on and so forth. So we approximate the control with an actor neural network. We approximate the cost with the critic neural network, and then we pick the tuning between these two. So the tuning, you can think they can be your favorite tuning laws. We pick gradient descent for the scenarios, and then eventually we can prove that we can learn the optimal gains for the optimal controller and the optimal cost.
Thank you. Thank you. Maybe it will be good if we can talk more.
Yes, definitely. Send me an email, and then I will send
Yeah.
you some representative papers. And then also, if you can send me some work that you have done in these drones, we will be happy to give you some hints if you want.
Thank you.
Yeah, so TeamWay's advisor is Jerome Darbon, who's working on controls, and so they together we combine to do like pins. So the Hamilton-Jacobi equation is used for the pins loss, and then there's some other things here. But now we're trying to do control of that, and we're thinking about how to include uncertainty, but in a different way. Like with the target would be uncertain. Would put in the models. We'll have let's say a model that we don't know exactly. You so you don't know the model at all. We want to know because we want to have the physics play a role.
No, of course.
Yeah. So we could contaminate the model, or we could have some other, like the object. If you go around objects, we don't know exactly the object, for example, when we So that's sort of roughly speaking what we are trying to do.
So we have done
you.
some learning of Gaussian learning Gaussian processes to learn the obstacles, to learn all these things. So actually, I have been also thinking about how to incorporate your PINNs into the Hamilton-Jacobi-Bellman equations and try to do similar, to do something like that. So
yeah, TeamWay will send you that paper, which shows.
If you can send me this one, I think there is lots of hanging fruits there. I think, and especially in controls, people they haven't really shown in an elegant way how you can bring this model-based and model-free, which is actually your PINN ideas. It's actually interaction of model-based and model-free techniques, and how you can use prior knowledge of the system, of the physics, and incorporate in your learning mechanism.
Yeah. Yes.
And I think there is lots of things there we can do, especially for control. So if you can send me the paper you guys have working with Jerome, I would appreciate, or TeamWay, or whatever.
Yeah, TeamWay will send. Yeah.
Very good.
Thank you.
Very good. Very good. So, any more questions?
It's really a good day here in the east, on the east. So people want to go out on Friday afternoon and play, I think.
Sure.
So,
I don't want to interrupt this beautiful day. So you guys enjoy. Again, thank you very much for this wonderful invitation. I really admire what you guys are doing with all these PINNs and all this great stuff. George, thank you very much.
Yeah,
so
thanks for stopping by.
Yeah. And Zongren, thank you very much. So, and everybody, thank you very much. So again, if you want to send an email, I will definitely get back to you probably in 5 minutes. So thank you. Thank you, everybody.
Yeah.
Enjoy your day and happy weekend.
Bye.
Bye.
So thank you everyone for tuning in, and we'll close the seminar today. Have a nice weekend.